Okay, so today I selected a few works on that I think are quite relevant for digital twins, and those are works on neural relightable assets. So let me first explain what I mean by this. So by asset I mean a 3D object that is sufficiently self-contained that can be inserted into any renderer, offline, real-time, web-based, with global illumination or without. So there are many methods that do relighting on images or videos, but they don't produce assets. So we are only going to look at the methods where the result is an asset, because that's the digital twin. So we would like the asset to be relightable, where we mean it's not just view synthesis that bakes some original lighting, original shadows, original highlights, but correctly responds to any new lighting in the scene where you insert it. Ideally, this should be like a 6D surface reflectance over position, incoming direction, outgoing direction over the whole object. And by neural, so I mean, the neural by itself it's not a feature, it's more like a tool. But really, what I mean is by neural is that the reflectance is learned rather than using some limited analytic model such as GGX. I mean, I'm a big fan of GGX, but after 20 years, it might be due for retirement. At least I think so. This is a controversial thing. You don't have to agree, but so this will be our assumption. We want the reflectance to be learned, and so I feel like if all these problems can be solved, then such 3D assets are ideal digital twins of real-world 3D objects. And of course, we can think about scenes and like 4D facial animation and so on, but the 3D objects are already hard enough, so let's start with those. So I'll talk about 4 recent methods. One is called RNA, Relightable Neural Assets. It will be presented at SIGGRAPH, even though it's the work has been around for a while. Then Relightable Neural Gaussians, which is work presented right here at CVPR 2025, which generalizes RNA to any geometry. The geometry doesn't need to be provided up front. And then freer hands, it's a variation of relightable neural Gaussians that works with a turntable capture under natural lighting, while the RNG needs special point light, like point lighting in a dark room. And then finally, Relit LRM is like a feed-forward a way to relight Gaussian objects, reconstruct and relight. So basically none of these are perfect. We can actually make a table like this. So the relightability is true for most of the methods, except for this freer hands method actually only allows light rotation. So that's not full relightability. All of them are neural. Don't make any GGX assumptions, anything like that. Most of them produce a standalone asset, but the LRM method actually doesn't, because every new lighting needs a new evaluation of the feed-forward model. Right? So you only get one asset for lighting. You can get a new lighting, but you have to rerun the inference. We would love easy capture, but it's not. Yeah, for some methods it's easier than others. Sparse views are easy, turntable is easy, but darkroom is hard, and so on. And we would like the quality to be high everywhere. So, the first thing I want to talk about is RNA relightable neural assets. This work, when we started it, we wanted something with full relightability, any material, all the shadowing, subsurface scattering, hair, fur layers. Actually, you can see this Lego. It's the old Nerf Lego, but we made it translucent. You can probably not notice that, just to kind of make the point that we can handle subsurface scattering, among many other things. But we assumed, okay, the geometry is given from somewhere else, because the problem is hard enough even with that assumption. So here's a scene of neural and classical assets rendered in a single, with GI and everything, reflections. You can tell which ones are neural and which ones are classical. The simple, easy ones are the classical. And indeed, it is relightable. So here, the lighting is rotating around the whole setup. So how does all of this work? So first, we kind of need to define more precisely what we mean by this reflectance field. I mean, it's like different people mean different things, but here what we mean is what is going to be the light leaving point X in direction omega out, assuming the whole object is lit by direction light from omega in. This is simple enough to define. We just need to be careful, like all the self-reflections and shadows are included. So when we compute the rendering integral, we only want the light beyond the asset. But that can be done. So the architecture here is actually, fairly simple. We assume ground truth geometry given to us from somewhere else. We just need to texture map it with features and then use an MLP to give us the, given a point, we query the feature, and we know the incoming and outgoing and a few other details, and it returns the final color. And the features can be done using a triplane. They can be done using other things. So there's this one improvement is that we can, instead of having the model learn all the sharp shadows, if we have ground truth geometry, we can just trace array. We know the shadow. We can help the network with the shadow. We can also use standard UV mapping to do the features. We could probably use other things such as hash grades. And anything that defines the features should work. So one thing is, the way I define the reflectance field is kind of like a far field approximation, but you may think that, okay, it's not going to work well with local lighting. Well, in fact, it works just fine. You can bring the point light really close to the asset and it still works pretty well, because it's kind of hard to break the assumption that like if a point is lit mostly from one direction, the points nearby they're probably still going to be lit from that same direction in normal situations. You can break it in like a lab setting, but yeah, so this works. And the result works, in real time on a consumer-grade GPU. You can use a point light. You can use environmental lighting. Use any lighting that the renderer supports, because the renderer just needs to know for a given point, given omega in, given omega out, what is the reflectance, and that's what the model provides. Mm-hmm. Though, of course, the one remaining issue is this geometry. We are assuming somebody gave us, Oracle ground truth geometry. So can we get rid of that assumption? So that's what the relightable neural Gaussians that is presented here does. So the way this works is, okay, so the full diagram looks complex, but most of the complexity is to render crisp shadows. And we had to do that to beat the PSNRs on previous methods and all that. But if you don't really care too much about having precise sharp shadows on your assets, then all of this is kind of like just some detail how to get really good shadows. So we can, most of this is shadow handling. The core of the idea is super simple. We have like standard Gaussian splitting, but instead of the spherical harmonics, we have a latent vector or feature vector per Gaussian, and we have MLP, a decoder that given feature and view and light gives us the reflectance, which I think this is really the right way to go. I think spherical harmonics like GGX, should go to retirement soon. And I think this is really the future. All assets should be represented, not necessarily with Gaussians. Could be other primitives, but you kind of want this MLP or small network giving you the reflectance. So here's some results. So these captures were done actually by a great previous paper called NR Hints from SIGGRAPH 23, so we use their data, but we fitted them with our method. Yeah, actually, and also like on synthetic data, it still works, and we have the ground truth, so you can see that it actually matches the ground truth really well on synthetic data too. So, okay, so that's, how am I with time?
Back. You have call?
Yeah, cool. There is still this problem with the relightable neural Gaussians, which is that the input is, you need many views with varying point lights in a dark room. And the way to do that is, normally you need two people in a dark room collaborating. Each has a phone, one of them is used as a camera, one is used as a flashlight. And that is, doable, but it's not something like a non-expert users would do on like their, e-commerce, some product they want to sell. So can we make the capture even simpler? That's the goal of this free your hands method, which uses a turntable plus a tripod to capture the object, a small number of views times a large number of, turntable rotations per view. And then, this, and all of this is under natural lighting, right? So there's nothing is known about lighting other than it's like regular lighting in an office. Now, of course, many people have used turntables, but turntables under unknown natural lighting are actually tricky. Actually, many people would find it even hard to see why this is not just view synthesis. Because you could say, well, you just run colmap, it gives you the pose of the camera with respect to the object, everything's fine. But actually no, because the lighting is rotating in the pose of the object. So it's a little trickier. If you only want view synthesis, this is kind of like an annoyance. But if you want relighting, actually you're getting more data because the lighting is rotating. So you can think about it this way. So you can think about a 2D space where one axis is view and one axis is light. So what traditional novel view synthesis is doing is basically taking a column here. One fixed light rotation and a bunch of views, right? So now you can think about what happens if instead you fix the camera and do one full rotation of the turntable. So what you get is kind of like in the frame of reference of the object, what you get is like a diagonal through this space. Right? So the light is changing, the view is changing, but they are tied together. So it's kind of like a diagonal. But then if you do multiple views and each will have a full turntable rotation, you kind of have like these multiple diagonals, striped through your domain. So now you're kind of filling in a good part of the domain that you could actually go and fit the function across the whole domain. And that's exactly what we do with an MLP. And it works really well. And you can, as a result, you can get novel views and novel lightings. But of course, the novel lightings are only novel rotations. So, and so you can then, play with your rotation afterwards on the asset, which is kind of a nice extra feature over, standard Gaussian splatting that would just give you view synthesis. And you can use it for harmonization, all kinds of things. But of course, it's not full relighting yet. We know that. There's a variant of the method Pang Wang from Adobe developed where instead of a tripod, you can actually hold it in your hand. And this is much easier than if there's no turntable. Because if there's no turntable, you have to go all the way around the object and not introduce any motion blur. And it's just way more work. But this is quite simple. And the results, given the same effort, the results are better than Gaussian splatting. And you can scan this QR code on the captured asset. I mean, it's just a little demo. So, I mean, one thing you can, of course, do, you can take multiple light rotations, take linear combinations of them, so you get new kind of cool lightings, like here, but this is not true relighting, but we are not far away, and this method, I'm kind of excited about this method because it has everything else. It's the capture effort is easy, the quality is super high. We just need one more step to make it fully relightable. So, yeah. So that's this free your hands method, and the final method I'm going to talk about is using a feed forward. I guess similar to previous talk, you can train a large model that works across objects to give you essentially relighting, reconstruction and relighting. So what Relit LRM is, it's a, well, I guess large is based on opinion, but it's a transformer-based architecture that takes 4 to 8 input views of an object, and it reconstructs the 3D geometry from them in terms of Gaussian splat positions, rotations, you know, all of that, and opacities. This step is similar to GSLRM. But then on top of this, for any given input lighting in terms, given as an IBL, well, actually, in fact, 2 IBLs at 2 different exposures, it computes the colors of under that lighting. Yeah, the results are quite good. I mean, they are, of course, the reconstruction quality will not be better than without relighting. Relighting will not make your reconstruction better, but the relighting quality is actually quite good. And the way the method works is it's kind of like a diffusion model but in the bottleneck of the diffusion, it's forced to create the colors on the Gaussian and render them. So there's a renderer in the loop of the diffusion. Actually, I can slightly simplify this. This beginning is exactly the same as GSLRM. It has nothing to do with relighting. So assume you're already given some geometry. You just need to figure out which colors should I put on the Gaussians. More precisely, which spherical harmonics should I put on each Gaussian, such that when I render it, I get the right result under that environment map. And so this works well, but you can also see the issue with this. The issue with this is that if you don't get an asset that you can just quickly render under new lightings. You have to rerun this entire model, which is actually a diffusion. It takes several seconds, but per new lighting per asset. So if you have a large scene with many assets, you won't be able to interactively render. So, but most likely this can also be solved. And then the other issue with this method is that it takes sparse views, that can be a feature, but say with the turntable I can easily get hundreds of views, low effort. And now I have hundreds of views, but I can't fit them in this method because the attention doesn't scale to so many inputs. So those are the kind of a few issues, but anyway, so let me show a few more cool results from this method. I mean, the shadows can be quite sharp. So the IBL resolution, I believe it's 128 by 64 or around there. And yeah, so you can get somewhat sharp shadows and, fairly high quality already. Okay, so I guess in summary, we can have a look at the table again, and I added one more column where I think definitely some method is coming very soon that will have all of these features I'm looking for. I don't know which method is the easiest one to start with. My feeling is the free your hands method basically already has everything other than it only does the rotations. So can we combine that with a feed-forward model to give us full relighting instead of just light rotation per Gaussian? But this is all up for you guys to think about. But I think like once all of these problems are solved, this is kind of the ideal representation for a 3D digital twin of an object. Cool, yeah, so thanks a lot.